In the darkness between stars, matter drifts for ages that have no measure in ordinary calendars until gravity draws it together and ignites a new star. Around one such star long ago, a disk of rubble and gas settles into circles, and from that disk the planet called Earth slowly takes form. Its crust cools, oceans collect, continents rise and sink, and with each rise and fall, the surface writes another page into a record that deep time keeps. Every buried layer of clay holds memories of fires, oceans, and vanished atmospheres. To most eyes, the rocks are silent. In the late 20th century, a geologist stands on a quiet hillside in central Italy, holding a thin chip of ancient clay. Above the layer lie fossils of mammals and flowering plants. Below it, remnants of a world ruled by great reptiles. Within this narrow band, no thicker than a human finger, rests a moment when almost all that lived on land and in the sea abruptly ended. The geologist measures the clay and finds an element that should be rare on Earth but common in wandering stones from space. Iridium, enriched far beyond normal levels, is locked inside the layer. The finding travels from hand to laboratory to journal, and slowly a new picture emerges. An object from deep space strikes Earth at tremendous speed, throws dust and fire into the sky, and leaves behind a scar large enough to hold a modern country. Dinosaurs fall, forests burn, oceans turn sour, and in the quiet that follows, small mammals begin a long rise. All of this is inferred from clues in stone and ash. One thin stripe in the rock preserves the violence of a single day, tens of millions of years in the past. The revelation does more than explain why giant reptiles vanish. It proves that the planet remembers. It shows that a brief and terrible event can leave a sharp signature that endures across immense spans of time. If an asteroid impact writes such a clear line, a further question forms. If an industrial civilization were to rise and fall, would it also leave such a mark? The modern age has already begun to etch its own story into the crust, the air, and the seas. Fossil fuel burning changes the balance between light and heavy forms of carbon. Synthetic materials drift into ocean floors and river deltas. Nuclear tests brighten the isotope patterns of certain heavy elements. Ice at the poles traps traces of soot, metals, and invisible gases that only factories and power stations release. To observers in some distant future, human industry becomes an instant in stone, a distinct band of altered chemistry and unusual particles between more ordinary layers. The thought extends in two directions. One looks forward, asking how long the human trace will last, and what name distant minds might give to this sudden shift. The other looks backward, deeper into the archive of rocks, and wonders whether something similar has happened before. The idea receives a name borrowed from imagined creatures in a long-running story of televised fiction. Researchers begin to speak of a hypothesis that asks whether an earlier industrial civilization might have risen on Earth long before primates evolved large brains or before the familiar lineages of present animals took shape. This proposal does not begin with claims of ancient machines or buried cities. It begins instead with signatures. Any technological society must use energy, concentrate resources, and alter its surroundings on scales large enough to support complex tools and vast populations. These actions leave traces that do not depend on the survival of buildings or metal traces that may persist after mountains are raised and worn down again. In sediment and chemical ratios, in the pattern of certain minerals, an echo of industry might endure long after the lives of its makers. The question becomes simple in form, but enormous in scope. If an industrial civilization existed deep in the past, what would its footprint look like now? And would present science already have mistaken that footprint for a natural event, Many geologists assume that the archive is already well read, that mass extinctions, abrupt climate shifts, and strange pulses of particular elements can be traced to volcanoes' impacts and the slow rearrangement of continents. Yet the planet is old beyond ordinary imagining, and the written pages of its story are incomplete. Erosion tears out chapters. Subduction drags whole sections back into the mantle. What remains at the surface is scattered, patchy, and biased toward the recent. In such a fragmentary library, a brief technological age might appear only as a thin chemical whisper. The hillside in Italy, the iridium-rich clay, and the crater hidden beneath younger sediments all stand as proof that a single day can carve itself into rock so clearly that minds far in the future can reconstruct it. The speculation that follows is quiet rather than sensational. If one catastrophe is preserved so faithfully, might other stranger episodes also be stored in less obvious ways? Somewhere in the stacked layers beneath deserts, oceans, and polar ice there may lie patterns that do not fit comfortably within any catalog of known natural processes. For now they remain largely unsearched, waiting for questions that have only just begun to be asked. In this beginning, the mystery is not that ancient machines are found, but that the rocks are eloquent and incomplete. The stage is Earth itself, its deep-time archives, and the possibility that intelligence has visited this stage not once but many times, each visit recorded in codes that modern science is only starting to learn to read. In laboratories, on drilling ships, and across quiet outcrops, fragments of Earth's history arrive on work tables and screens. Each core of mud, each slice of limestone, each grain of volcanic ash carries information about conditions long vanished. Under microscopes, tiny shells appear layered one upon another like the rings of a tree. Even with all these samples, the story that emerges is full of interruptions. Whole regions of time seem to thin out or vanish, replaced by sudden appearances and disappearances of new forms. Paleontologists speak of the fossil record as if it were a book, but when they turn its pages, they find that most of them are missing. Only scattered paragraphs survive preserved where chance allowed bone shell or imprint to escape decay. In the earliest chapters of that book, the narrative grows especially strange. For a long stretch, only simple cells appear modest in shape and function, leaving behind little more than chemical hints of their existence. Then, within a comparatively narrow band of time, more than 500 million years ago, the pages become suddenly crowded, skeletal parts harden, eyes form, limbs articulate, mouths develop teeth. This flourishing of complexity, known as the Cambrian explosion, transforms the seafloor from a mostly quiet terrain into a realm of hunters and prey. The change does not occur in a single instant, yet in geological terms it is abrupt, compressed into a span that feels more like a surge than a slow evolutionary drift. Researchers suggest that the apparent suddenness may be an illusion born from poor preservation. Soft bodies rarely fossilize, and early ancestors may have lived and vanished without leaving sturdy parts behind. Sediments that once held intermediate forms could have eroded or been drawn down into the mantle. Yet as more sites from this period are found across different continents, the pattern remains stubborn. Lineages emerge already distinct. Their body plans establish their ecological roles clear. It is as if the narrative of life turns a page and finds an entirely new cast already on stage. The explanation may still lie within natural processes. Shifts in oxygen levels, changes in ocean chemistry, and the opening of new ecological spaces could all have combined to favor rapid diversification. But because the event is so sharp, some minds begin to ask whether other forces might also have played a role, forces that leave subtler marks than impacts or lava. The Silurian question quietly extends itself. If an earlier technological culture once existed, could it have guided or accelerated biological change? Gene-level interventions would not leave fossils of tools, but they might imprint patterns on the timing and character of evolutionary leaps. The fossil record alone cannot answer such a suggestion, yet it provides context. After the Cambrian richness unfolds, other leaps and losses follow. Mass extinctions punctuate the record, wiping out the majority of species, then opening room for new waves of life to appear. Between these collapses, there are quieter intervals during which lineages refine themselves, ecosystems thicken, and continents drift. Through all of this, the physical archive of rock remains uneven. In some regions, hundreds of meters of sediment stack gently, preserving an almost continuous record. In others, uplift and erosion scrape the surface clean, leaving only thin remnants that skip across millions of years. If a technological episode unfolded during one of these poorly recorded intervals, its direct traces might be gone, but indirect consequences could remain. Unusual patterns in extinction, sudden shifts in atmospheric composition, or global pulses of certain elements might hint at large-scale activity. Enormous volcanic events and the rearrangement of continents can account for much, but not always for the speed of some changes. A smaller number of researchers thinking along Silurian lines treat these puzzles as places where alternative possibilities can be quietly tested. They imagine scenarios in which energy-hungry cultures alter atmospheric chemistry, mine the crust, and redirect water, then vanish, leaving only a ripple in the deep statistics of rock and fossil. In such scenarios, intelligence does not stand outside geology, but becomes one of its agents, as wind, river, and magma already are. To test such ideas, one must ask what a civilization truly is when stripped of cities, languages, and machines. At planetary scale, it becomes a pattern of energy flow and matter movement. Forests cleared, hydrocarbons burned, metals concentrated and scattered. These processes enforce their own physics regardless of who or what initiates them. Whether driven by primates, cephalopods, or some now vanished lineage, the signatures would share broad similarities because the planet responds according to its own rules. This realization makes the search both simpler and more elusive. Instead of scanning for any possible anomaly, researchers can define a few core expectations: concentrated pulses of greenhouse gases, manufactured isotopes, if nuclear reactions are harnessed, synthetic compounds, or unusual distributions of metals and minerals. Yet the deeper into time one peers, the more these signals blur under heat pressure and mixing. By the time hundreds of millions of years have passed, only the broadest strokes may remain distinguishable. In this way, the fossil record and the geochemical record together create a kind of half-lit corridor. In its dimness, sudden appearances of new life, sharp breaks at extinction boundaries, and swift swings in climate stand out like silhouettes. Whether those silhouettes are cast by entirely natural forces or by an earlier round of technological activity remains an open question. For now, the corridors of stone invite careful walking and patient reading. Within that partial memory there may rest more than one story of minds that arose, acted, and were folded back into the quiet rock. High in polar latitudes where air thins and cold grips the surface, ice builds itself into archives. Snow falls, traps tiny grains of dust and faint traces of gas, then compresses into layers that stack through hundreds of thousands of years. Each layer keeps a sample of the atmosphere that floated above it when it formed. Teams travel to Greenland and Antarctica, set up camps on pale plateaus, and drill slender cylinders down through the ice. When the cores arrive in laboratories, instruments hum, and the ancient bubbles are coaxed from their crystal prisons. Within these tiny volumes of air, the ratios of gases reveal patterns of climate swings, volcanic episodes, and subtle shifts in the balance between life and rock. Among the tracings of natural rhythm, new forms of change stand out. In the most recent sections, carbon dioxide rises with unusual speed, methane climbs, nitrous compounds drift upward, and traces of synthetic substances appear that did not exist in earlier ages. These are the signatures of an industrial civilization in full operation. Future readers of the ice would see this as a sharp deviation, a sudden tilt in what had been a slow oscillation governed by orbital cycles and feedbacks between ocean cloud and forest. The realization that such a brief period can be clearly written into ice leads to another question. If modern civilization can carve its presence into the climate record in only a few centuries, what similar disturbances might lie deeper down in time? The reach of ice cores is long but not endless. The oldest clear records extend back close to 1,000,000 years, a span vast by human standards, but small compared with the age of complex life. Beyond that, older ice flows and deforms until its fine structure vanishes. For earlier chapters, attention must shift from frozen water to stone and sediment. On the floors of oceans, particles rain down year after year. Tiny shells made by plankton settle alongside dust from deserts, ash from eruptions, and traces of chemicals carried by rivers. Over millions of years, these layers harden into mudstone and chalk, storing within them the chemistry of the waters that once covered them and of the air that touched their surface. When drills bite into these deposits and cores rise to daylight, geochemists read them for clues to ancient atmospheres. A central part of that reading involves isotopes, which are versions of the same element that differ slightly in mass. Carbon, for example, comes in lighter and heavier forms. Life tends to prefer the lighter version, so when large amounts of organic matter are buried or burned, the balance between the isotopes in air and sea shifts. Each process leaves its own pattern of change. In several episodes scattered through the last few 100,000,000 years, the rocks record sudden pulses of light carbon entering the system. These pulses mark times when the climate warmed rapidly, oceans grew more acidic, and many species struggled. One such event near the boundary between the Permian and the Triassic periods is particularly intense, as if a huge store of ancient carbon had been released in a geological instant. Standard explanations point to massive volcanic provinces that erupted for long intervals, pouring out lava and releasing greenhouse gases with methane hydrates, perhaps adding their own warming effect. Yet the magnitude and speed of some changes prompt quiet curiosity. The pattern bears an uneasy resemblance to the modern industrial pulse of carbon scaled up and spread over a longer interval. It does not prove that industry drove those ancient shifts, but it does sharpen a sense of what to look for. If a technological society consumed large stores of reduced carbon, whether coal-like deposits deep petroleum or some other reservoir, it would leave behind a distinctive isotopic fingerprint. That fingerprint would appear as a rapid influx of light carbon followed by a slower return toward previous values as natural processes drew the excess back into rocks and deep waters. Linked to this would be changes in oxygen, in ocean acidity, and in the distribution of certain elements. In the human era, industrial activity also creates molecules that never existed before. These substances are rare but long-lived, and they have strong effects on atmospheric chemistry. If earlier civilizations developed their own families of synthetic molecules, the direct traces would likely not persist over tens of millions of years. Complex organics break down and rearrangements under heat and pressure erase fine details. Yet their presence could have nudged climate and high atmosphere chemistry. in ways that produce secondary signals, perhaps in unusual patterns of nitrogen or chlorine within mineral deposits. Throughout these inquiries, a tension persists between the completeness of physical law and the incompleteness of surviving evidence. Natural explanations exist for every anomaly so far described, yet the range of natural processes is itself learned from the same imperfect rocks and cores that are under examination. The histories that ice, mud, and stone preserve show that the planet is sensitive to relatively brief disturbances. They also show that after even the most severe disruptions, climate and chemistry eventually slide into new balances, and the detailed causes of the initial shock grow harder to reconstruct. In that fading space opens for speculation. Intelligence, if it rose, flourished, and disappeared, would leave signatures broadly similar to those seen today. Whether any of the ancient pulses and shifts now known represent such a story remains unknown, but the act of asking reshapes the way the geologic record is read, turning it from a static catalog into an active field of clues, where each layer might carry more than one meaning at once. On coastlines and river mouths and far from land on the abyssal plains, modern industry leaves behind fragments that do not occur in nature. Pieces of plastic bags, threads from synthetic fabrics, beads, once used in cosmetics, and films shed by packaging all drift downward and become part of the sediment. Under magnification, these fragments appear as bright shards and fibers alien among grains of quartz and the fragile shells of plankton. They resist decay, persist in cold darkness, and mix into layers that will one day harden into stone. Along with them sink particles from smelters, power stations, and engines, tiny spheres of metal and glassy ash formed in high-temperature furnaces. Each carries a story of combustion and refinement. To a future geologist, this mixture would stand out as a sharp horizon, a moment when the sediment suddenly gains new textures and chemistries. Plastic in particular becomes a quiet marker of technological presence. Its long chains of carbon and hydrogen, often decorated with chlorine, fluorine, or other elements, do not match the patterns made by simple organic decay. Yet over millions of years, even these durable chains may crack and reform under heat pressure and mineralizing fluids until only their influence on local chemistry remains. When researchers consider the possibility of earlier civilizations, they wonder what analogs to plastic those cultures might have produced. Perhaps they formulated polymers with backbones that survive even longer, or materials designed to vanish quickly, leaving almost no direct residue. In either case, the chance of finding recognizably manufactured fragments after tens of millions of years is small. What may persist instead are the byproducts of processing. Modern high-temperature industry reshapes metals into forms that cool into characteristic microstructures. Fly ash from coal plants and other combustion sources solidifies as smooth spheres with textures distinct from volcanic glass. Today, these artificial spheres accumulate in soils and sediments downwind of industrial regions and in distant oceans. If similar particles appeared in unexpected abundance within ancient layers, their origin would demand explanation. Natural fires, lightning strikes, and volcanic eruptions can create limited amounts of such glassy forms, but widespread distributions linked across continents would hint at something more organized. Another family of markers arises from experiments with the atom. When reactors operate and weapons are tested, they shift the balance of isotopes in ways that do not occur in purely natural chains of radioactive decay. Some of the artificial nuclides have half-lives long enough to persist as subtle signals for hundreds of thousands or even millions of years, especially if they are quickly buried away from circulating waters. In human times, these isotopes are carefully tracked as indicators of fallout and fuel use. In deep time, mixed into rocks and clays, they would appear as slight but telling enrichments against a background shaped by older stellar residue and by natural reactors such as those that once operated in ancient ore bodies. The discovery of such a natural reactor in Central Africa proved that under specific conditions uranium deposits can reach criticality and sustain fission without human design. That finding both widened the known range of natural nuclear phenomena and sharpened the criteria by which artificial activity might be recognized. A natural reactor has a particular geometry, mineral context, and suite of byproducts. Deviations from those patterns in unexpected settings become places where questions gather. So far, no confirmed signs of ancient engineered fission exist, yet the mere existence of nuclear processes in the deep past makes the geologic record a place where the distinction between natural and constructed must be drawn with care. This interplay between possible natural and possible artificial causes runs through the entire search. For every anomaly considered as a potential trace of industry, there are volcanoes, impacts, meteorite showers, and ocean anoxic events that might create similar signatures. Clusters of metallic spherules could come from cosmic dust. Strange carbon patterns might mark the bloom and decay of methane-producing microbes. Even elevated concentrations of particular metals can reflect the slow action of hydrothermal vents over millions of years. The Silurian line of thought does not seek to replace these explanations, but to test them to ask whether there remain residues that stretch them beyond comfort. In practice, this means scanning for combinations, a layer where carbon isotopes swing rapidly, synthetic-looking spherules thicken the sediment, and heavy elements appear in unbalanced proportions. It means looking for sequences in which climate chemistry and extinction move together in ways that echo what is now unfolding under human influence. The task resembles listening for a familiar melody faintly repeated in an older symphony. Even if the notes are blurred, their pattern might still be heard. Under this view, the modern world becomes a template. The spread of plastics, metals, and long-lived isotopes creates a reference horizon. By charting precisely how these markers integrate into mud, ice, and rock, scientists can better estimate what survives and what vanishes over specific spans of time. From those estimates, they can turn backward and ask with more discipline what kinds of traces an earlier age of technology would leave and whether current cores and cuts have already sampled the relevant intervals. For now, most evidence remains consistent with known natural processes, but the search itself alters perception. Where earlier generations of geologists saw only volcanoes and impacts, some now also see the abstract possibility of machines and reactors long gone written not as artifacts but as altered atoms and grains. Between subduction zones that recycle crust ice sheets that scrape surfaces clean and oceans that dissolve or bury the planet is skilled at forgetting, yet it never forgets completely. Some fraction of every event becomes part of the slow building of new stone. Somewhere in those depths, there could be thin bands where nature and technology once entwined so tightly that their traces are now inseparable, waiting for methods subtle enough to untangle their story. Deep beneath old continents, miners and geologists follow seams of ore into the bedrock, tracing the slow concentration of heavy elements that water and chemistry have gathered over eons. In some places, veins of uranium run through ancient rocks, remnants of a time when the element was more abundant in the crust and more radioactive than it is now. In the early 1970s, workers in a mine in equatorial Africa send samples to be assayed for fuel. and analysts notice that the ore is subtly depleted in a particular isotope. The pattern looks as if part of the uranium has already undergone fission, as if a reactor has secretly run and then shut down billions of years before any human built such a device. Investigations reveal that natural conditions once allowed groundwater to flow through the ore, moderating neutrons and turning that pocket of rock into a self-sustaining chain reaction. For hundreds of thousands of years, the stone itself functions as a reactor core. The discovery proves that nuclear processes do not always require conscious design. Under rare but possible alignments of geometry, composition, and water, the planet can build its own reactors in the dark. The byproducts of these reactions, preserved as isotopic anomalies, remain legible even after most of the original heat and radiation have faded. This lesson cuts both ways. It shows that some signatures once thought to be proof of technology can arise without it, and it also confirms that fission leaves distinct, durable marks that persist across immense spans of time. In the modern era, nuclear weapons tests loft rare isotopes into the stratosphere, where winds spread them across the globe. Some fall on ice and snow, some sink into oceans, some become fixed in soils and lake sediments. Power plants add their own contributions. The pattern is complex, but recognizable specific ratios of isotopes that do not match any natural decay chain spikes and elements that do not form in ordinary stellar processes and distributions that trace human geography rather than geology. Future readers of the record would see a brief, sharp, and planet-wide experiment with the nucleus, a thin interval in which one species reached into the deep structure of matter and rearranged it. When the Silurian idea turns toward the nuclear realm, it asks what similar experiments might look like if they happened long ago. Natural reactors such as the one in Africa occur only under narrow constraints. Their waste products cluster in limited volumes and are enclosed in particular minerals. In contrast, a technological reactor can be moved, buried, dismantled, or destroyed in many settings, leaving fission products in configurations that differ from the tidy geometry of a self-assembled core. Weapons tests concentrate fallout in particular atmospheric layers. Reprocessing plants can leak mixtures of isotopes into rivers and coastal sediments. Underground detonations fracture rock and melt pockets of glass whose chemistry bears the mark of both local minerals and injected energy. Over millions of years, many of these localized features would erode or be subducted. Yet some fraction of their signal could remain, especially in stable shield areas where erosion is slow and burial steady. Geochemists thinking along these lines sometimes re-examine measurements and ask whether any known deposits show isotope patterns that do not fit comfortably within natural explanations. Small anomalies have been reported, but each has so far found a place within the broad range of known processes. In this ambiguity, the nuclear record mirrors the broader geological one. It is full of suggestive patterns that lean toward natural explanations while never quite closing the door on other possibilities. If a technologically adept species once walked the planet in some remote era, turning uranium into heat and light, part of its story would lie in how it managed the wastes. Long-lived isotopes present challenges that encourage burial in deep repositories, dilution in oceans, or in some imagined practice, transmutation into more benign forms. Deep repositories would be most visible if preserved because they gather many isotopes into one place, but they would also be targets for later tectonic disruption. Ocean dispersal spreads the signal thinly but widely. Active transmutation could in principle erase many direct traces, converting dangerous nuclides into stable ones that blend with the background of ancient stellar debris. Even in that case, the energy and material flows required for such work might leave secondary marks in heat budgets or unusual distributions of daughter elements. The modern nuclear age thus serves as both model and mirror. It shows how easily a brief period of intense activity can leave planet-spanning hints, and it shows how incomplete the record will look after enough time has passed. Already in only a human lifetime, reactors have been dismantled and test sites weathered. Wind and water soften craters. Yet in the fine grain of rock and ice, the altered ratios of cesium, strontium, plutonium, and other elements quietly persist. The contrast between the visible and the invisible deepens the sense that any search for ancient reactors must be patient and indirect, focused less on obvious ruins than on quiet shifts in the ledger of atoms. Somewhere in rocks not yet sampled, there could exist a layer where isotopes align in a way that looks less like a natural reactor and more like a fuel cycle, a sequence of enrichments and depletions that suggests planning. Until such a pattern is found, the nuclear past of Earth beyond known natural reactors remains an open field of possibility, bounded by physics but not wholly mapped by present evidence. The rocks keep their counsel, remembering fission across long ages and standing ready to record without preference whatever future minds choose to do with the forces locked inside the nucleus. Energy flows through a civilization like blood through a living body, invisible from a distance yet decisive in how that body moves, builds, and changes its surroundings. On Earth, most large-scale energy ultimately begins as sunlight or as the slow release of planetary heat. Life captures a fraction of that flow in bonds of carbon and hydrogen. Over vast stretches of time, dead organisms sink into mud, are buried, and become coal, petroleum, and gas. These concentrated stores are the compressed history of ancient forests and plankton blooms waiting in darkness. When an industrial species discovers them, it uncorks time. In the current era, wells and mines bring this stored carbon to the surface and burn it in furnaces, engines, and power stations. The heat drives turbines, the turbines drive machines, and the machines rearrange landscapes. Smoke rises, exhaust accumulates, and the atmosphere's balance of gases shifts. Instruments record a steady climb in carbon dioxide and methane, a tilt in the isotopic mix that reveals the fossil origin of the added carbon. The oceans absorb much of this excess, growing slightly more acidic. Ice retreats, seasons change, and climate patterns drift into configurations no human ancestors ever knew. In a few centuries, a species has altered conditions that took millions of years to establish. From a geological viewpoint, the change is nearly instantaneous. The record that forms in this interval is not only chemical, but structural. Coral reefs built in warmer waters differ from those in cooler seas. Lakes form or dry out. Desert belts move. On land, pollen preserved in peat and silt chronicles the spread and decline of different kinds of vegetation as temperatures and rainfall shift. Together, these strands weave a distinct layer, a horizon in which the planet's energy and matter flows are rerouted by one lineage's choices. When thinkers consider hypothetical past civilizations, they imagine similar shifts scaled to different technologies and times. If an earlier society chose organic fuels, its energy use would leave a carbon imprint akin to the modern one, though perhaps peaking at different strengths and spanning longer or shorter durations. If it tapped deeper planetary heat or tidal forces, the signals might be subtler, perhaps encoded more in patterns of resource depletion than in atmosphere alone. More advanced methods, such as controlled fusion, would produce fewer long-lived chemical traces, yet even there, the supporting industry might leave a fingerprint in mining scars, waste heat, and altered distributions of certain light elements. Climate in all cases would respond. It is sensitive to sustained imbalances. A civilization that managed its energy flow without ever disturbing this balance would be nearly invisible in the stratigraphic record, but such perfect equilibrium seems unlikely for any young technological culture. Surges in energy use tend to precede surges in population, infrastructure, and material throughput, each of which amplifies the original disturbance. Some researchers therefore look for patterns not only of change but of overshoot and recovery. They search for intervals where temperature rises abruptly, stabilizes for a time, then falls almost as quickly, perhaps in concert with signs of ecological stress and rapid reorganization. These wave-like profiles echo what models predict when societies expand to the limits of their resource base, strain the environment, and then contract. In the modern world, discussions of climate engineering further sharpen these comparisons. Proposals to scatter reflective particles high in the atmosphere, fertilize oceans to draw down carbon, or build large networks of machines that directly remove greenhouse gases all have distinct signatures. Particles might alter the ratio of sulfur or other elements in polar snow. Ocean fertilization could leave an imprint in the pattern of organic matter and oxygen in deep sea muds. Direct capture at vast scales could slow or reverse isotopic trends. If analogous projects were undertaken long ago, they too would leave coordinated changes, multi-layered fingerprints in air, water, and rock. The challenge lies in separating these from the already rich tapestry of natural variability. Volcanoes also loft reflective aerosols. Orbital cycles rearrange climate zones. Biological innovations, such as the rise of oxygen-producing microbes, have already transformed the atmosphere once. Each known mechanism has its characteristic rhythm and geographic spread. Technological interventions would add new rhythms on top of these, tuned to the growth and decision-making cycles of conscious planners, rather than the slow beat of celestial mechanics. To glimpse such patterns, scientists combine cores from many locations, stacking their signals to see which fluctuations share a single global timing. Within those composite curves, one can see past ice ages advance and retreat, see intervals when tropical conditions creep poleward, and see sharp spikes where massive eruptions or impacts intervene. As the line sharpens, some odd intervals stand out where causation is not yet fully assigned, where warming or cooling seems to run ahead of or lag behind its expected drivers. They may ultimately find entirely natural explanations, but they also mark places where the Silurian question can be quietly posed. If an earlier civilization used great quantities of energy, experimented with its climate, or stumbled into feedbacks, it did not foresee these are the kinds of shadows it would cast. In the end, the planet's energy ledger is precise even when its archivists are incomplete. Every unit drawn from ancient fuels or harvested from wind and tide must flow somewhere, must warm some layer or move some mass. The visible edifices of a civilization may crumble, but its rearrangement of energy and matter remains woven into the long memory of Earth, waiting in stone ice and chemistry for any future intelligence patient enough to read it. Life itself carries a record that does not sit in stone or ice, but travels through time inside cells. Every organism on Earth inherits molecules of deoxyribonucleic acid from ancestors' long chains of coded units that store instructions for building bodies and running metabolisms. Over generations, copying errors and transfers slowly alter these sequences. Natural selection favors some changes and discards others, while chance drifts many into or out of existence. Biologists read these patterns as if they were marks along a clock. By comparing the genes of distant lineages, they estimate when those lineages diverged and reconstruct a branching history of life that stretches back billions of years. In this genetic tree, some branches lengthen smoothly, accumulating differences at roughly steady rates. Others show bursts where many changes cluster in short spans of time. These bursts can signal episodes when environments shift quickly or new ecological opportunities appear. They can also signal events when foreign genetic material floods into genomes from viruses or from symbiotic mergers. When the Silurian idea glances at this genetic archive, it wonders whether there could also be signatures of deliberate alteration. Modern genetic engineering already leaves faint marks. Modified crops carry recognizable patterns where natural genes have been rearranged or replaced. Laboratory insects and mammals bear inserted sequences that do not match any known wild ancestor. If samples of these modified organisms were somehow preserved for millions of years, their genomes would reveal clear traces of design, though their physical forms might seem ordinary. Over longer periods, however, the clarity of such signatures fades. Mutations accumulate on top of the engineered changes. Sections may be deleted or copied elsewhere. Recombination with wild relatives blends artificial and natural sequences. Eventually, only certain statistical oddities remain, such as clusters of changes that appear improbably well-tuned, or combinations of traits that arise together with unusual speed. In the present, biologists often encounter natural systems that feel almost engineered. Molecular machines in cells assemble and disassemble elaborate structures. Regulatory networks turn genes on and off in intricate cascades, yet all of these can be traced, however tentatively, to chains of intermediate states. Their parts show kinship with simpler predecessors, and their distributions across species fit known patterns of descent. For an ancient engineered feature to be distinguishable now, it would have to either resist erosion by mutation or be continually maintained by selection. One place where such resilience might occur is in core informational structures. The genetic code, the mapping between three-letter units, and the amino acids they specify is nearly universal across all life. Its particular arrangement has properties that reduce the impact of certain errors. Some researchers have speculated that this optimization might reflect a frozen choice early in evolution when alternative codes competed and one prevailed. A more radical speculation would ask whether such a code could have been tuned by intelligence. There is at present no compelling evidence that it was. Similar patterns can arise from blind trial and error operating over immense spans. Yet the question illustrates how deeply an engineered feature could sink into biology, becoming part of every lineage that follows. Another potential class of signatures lies in what does not appear. Evolution explores many possibilities, but its path is constrained by history. Anatomies and metabolisms arise from what came before, not from what might be optimal in the abstract. If an earlier civilization undertook large genetic projects seeding whole groups of organisms designed for particular roles, it might leave behind ecosystems that display echoing architectures. Entirely different branches of the tree of life could end up sharing complex arrangements of traits that under ordinary pathways would be unlikely to converge. So far, patterns of this magnitude have not been seen. Ancient deoxyribonucleic acid extracted from permafrost cave sediments and fossils adds another layer to the picture, but its reach is short. Molecular bonds break with time. Background radiation slices strands. Heat speeds decay. Under the best conditions, intact sequences rarely survive more than 1 million years. Beyond that, only fragments and chemical shadows remain. The deeper history of life must be reconstructed from living genomes and from fossils, not from direct genetic samples. This temporal limit means that if a technological species flourished tens or hundreds of millions of years ago and rewrote genomes on a grand scale, its specific edits would be difficult to distinguish now from the tangled record of ordinary evolution. The engineering would have blended into the background, its once sharp edges rounded off by mutation and selection. Yet the possibility invites biologists to think differently about what they see. Instead of assuming that all bursts of change are purely environmental in origin, they can at least entertain the idea that some might involve agency, however remote. That shift in perspective does not assert that such agency actually operated. It simply widens the conceptual space in which explanations are sought. The body of each living creature then becomes not just a product of blind processes, but also in principle a potential message carrier, a place where information beyond raw survival value might have been hidden. Some speculative thinkers imagine that an earlier civilization facing its own end could have embedded durable records into genomes, trusting that future intelligences would eventually decode them. Short, repetitive sequences or patterns in non-coding regions could, in theory, serve as storage. Whether such a strategy would survive deep time is doubtful, but the idea illustrates a broader theme. Biology is both participant in planetary history and archive of that history. Its molecules echo past climates, past catastrophes, and perhaps in some barely traceable way, past minds. Far below the surface, beyond the reach of ordinary weather rocks, grow slowly in the dark. Fluids seep through fractures carrying dissolved elements that join into crystals. Over millions of years, these crystals assemble themselves into patterns dictated by chemistry and pressure. Each atom finds its place according to the rules of bonding and charge, and the result is a repeating lattice, a rigid but intricate arrangement that endures long after mountains above have risen and worn away. In these lattices, information is already present in a simple sense. The spacing of the atoms, the presence of trace impurities, and the sequence of growth zones record conditions at the time of formation. Under microscopes and with beams of particles, geologists read these records to learn about ancient temperatures, fluids, and stresses. A crystal that seems uniform to the unaided eye can hold within it a layered memory of its own growth like rings hidden in transparent wood. Modern technology has begun to use this quiet capacity in deliberate ways. Optical fibers guide light along paths set by glassy structures. Tiny defects in diamonds store quantum states that can, under carefully controlled conditions, act as bits in a computer. Magnetic domains in minerals remember the direction of Earth's field at the time they cooled from molten rock, allowing paleomagnetists to reconstruct the wandering of continents. These examples show that geology and information are not strangers. They also suggest to speculative minds that a very advanced civilization might choose the deep crust as a long-term storage medium. Instead of carving messages on exposed stone or building libraries that erosion would quickly erase, it could tune the growth of crystals, guide impurities, or adjust isotopic compositions in ways that remain stable across hundreds of millions of years. The resulting archives would not look like machines, they would look like ordinary mineral deposits, their artificiality apparent only in precise measurements of structure and composition. Already some materials used in electronics blur the line between geology and device. Silicon wafers grown with extreme purity and doped with controlled impurities are cousins of natural quartz. Layers of different oxides and metals form structures that guide electrons in intricate paths. All of this exists at scales that are difficult to see without special instruments. If such patterns were somehow fossilized, if continents shifted and seas advanced and retreated above them, later geologists might break the rock and find only a strangely zoned crystal or a banded vein that does not fit standard classifications. The Silurian line of thought extends this notion further into the idea of mineral-based computing and sensing systems that operate on huge scales and long times. It imagines networks of crystals that respond to stress and temperature, transmitting signals through subtle changes in electrical properties. In essence, the planet itself could be turned into a slow, vast apparatus for monitoring and recording its own behavior. No such systems are known to exist, and the physics needed to maintain them across geological time is uncertain. However, certain natural minerals do exhibit behaviors that resemble primitive sensing and memory. Some change their structure when stressed, then retain that change. Others alter conductivity when exposed to different chemical environments. In laboratories, these properties are exploited in sensors and data storage devices. The leap from these small applications to continent-scale networks remains firmly in the realm of imagination, yet it frames a new way to think about possible technosignatures that are not made of metal and plastic. If a previous technological species wished to leave messages for distant successors, it might choose to encode them in such durable substrates. Information could be hidden in sequences of trace elements, along growth zones, in repeating ratios of isotopes, in layered deposits, or in patterns of defect densities that only precise tools could detect. From the standpoint of deep time, such strategies are attractive. They rely on the same robustness that makes ordinary rocks reliable recorders of climate and magnetic field, but they also carry challenges. Tectonic forces can heat and deform rocks enough to erase fine structures while leaving gross composition intact. Fluids can alter minerals, washing out carefully arranged impurities. Metamorphism can reorder lattices or recrystallize entire volumes. Any message written in this way would need to be redundant, distributed, and perhaps self-correcting, much like biological genetic codes are. In the present, some researchers explore the broad concept of in situ geological data storage, not as a legacy from ancient mines, but as a technology for the future. They study how radiation tracks in minerals might encode sequences, how arrangements of stable isotopes could mark particular eras, and how engineered crystals might act as both sensor and archive in environments too harsh for conventional devices. Though these projects serve current human needs, they incidentally highlight how an old planet might already carry layers of structured information that are not yet recognized as such. The boundary between natural and artificial becomes hazy when both operate under the same physical laws and use the same materials. A completely natural crystal can show patterns that are complex and unexpected, especially when growth conditions shift. Conversely, a deliberately modified crystal can be made to appear entirely ordinary and bulk tests its artificiality hidden in tiny deviations that only specialized methods can see. For now, the search for ancient civilizations focuses more on broad chemical and sedimentary anomalies than on intricate mineral structures. Yet as instruments improve, capable of mapping atoms within crystals and tracing individual defects, the possibility of reading deeper kinds of memory in stone grows. It remains more a question posed than a program pursued. If someone long ago chose to whisper into the crust, what form would that whisper take, and could it still be heard? The rocks that underlie continents have already watched several complete cycles of ocean opening and closing. They have seen supercontinents assemble and break apart. Within them, the silent choreography of atoms continues, indifferent to the stories that might one day be read there. Whether those stories are purely those of temperature and strain, or also in some faint layer of intention, remains an unresolved part of the larger mystery that the Silurian hypothesis invites minds to contemplate. Far from shore, where waves at the surface throw white foam, but their energy fades long before it reaches the bottom, the seafloor lies in perpetual stillness. Dust plankton remains tiny shards of shell, and the faint ashes of distant fires all settle through dark water in a slow and constant rain. In the deepest basins and trenches, this rain is the main sculptor. Storms do not scour it, rivers do not plow it, and strong currents rarely disturb more than the uppermost grains. Over hundreds of thousands and then millions of years, layers of mud build up each thin sheet, preserving a sample of whatever the world above was doing at the time. Because of this quiet ocean, sediments become one of the most faithful archives of planetary history. Drilling vessels anchor above key sites and lower hollow pipes through kilometers of water to bite into the seabed. The cores that return carry color bands and subtle shifts in texture that, when analyzed, reveal changes in temperature and chemistry. Tiny shells show how acidic the oceans were when they grew. Grains of wind-blown dust betray the strength of ancient deserts. Volcanic ash layers track eruptions that once darkened skies. Among these natural signals, modern industry is already leaving its own imprint. In upper layers, there are fragments of plastic industrial soot and increased concentrations of many metals used in technology. Ship paint, fuel residues, and particles from coastal cities all find their way here, mixed into the slow accumulation. If human civilization ended, the record of its influence would still continue to thicken as this disturbed upper layer is slowly buried by more ordinary mud. To anyone in a far future age reading downward through the stack, there would be a boundary where the composition of the sediment abruptly changes a horizon of altered chemistry, marking the brief moment when one species transformed coastlines, river loads, and atmospheric fallout. When the Silurian hypothesis looks at this scene, it asks what similar horizons might be buried far below in layers that formed long before humans evolved. Ocean cores from some intervals already show puzzling features. There are thin bands rich in certain metals such as iridium that point to asteroid impacts. There are black shales where organic matter is so abundant that it suggests widespread ocean stagnation. There are periods when carbonate shells dissolve, leaving gaps in the fossil record and hinting at episodes of sharp acidification. All of these have natural explanations, yet each also resembles in some broad way what a large-scale technological disturbance might produce. Imagine a civilization that chose the ocean as its main stage. It builds its cities on continental shelves, taps energy from tides and thermal vents, and disposes of wastes into deep basins. Its solid structures stand for tens of thousands of years before plate motions and erosion begin to dismantle them. On that timescale, many buildings crumble and vanish. Over millions of years, only a trace remains, not as recognizable ruins, but as slight enrichments of particular elements, unusual distributions of alloying metals or layers of glassy fragments weathered into sand. In the deepest trenches where pressure is immense and sunlight never reaches preservation, can be even more complete. The water is cold, biological activity is low, and burrowing creatures are scarce. There, any heavy object that falls may be quickly covered by fine sediment and left undisturbed for long periods. Exploratory submersibles sent into these depths have sometimes found unexpected features, fields of manganese nodules shaped like cobbles terraces, where currents sculpt soft mud, and occasional pieces of modern debris that have sunk from the surface. So far, every structure mapped in detail has proved to have a straightforward geological or recent human origin, Yet only a small fraction of the deep sea floor has been imaged closely. The rest remains as lines on charts. From a speculative viewpoint, this gap in coverage is an open door. If ancient technological constructions once dotted the ocean floor, they would now be buried, tilted, or broken, their materials altered by chemical exchange with seawater. Only their influence on local geology might persist. For instance, a large complex made of dense alloys could subtly change the way sediments drape across a region or seed the mud with a distinctive suite of corrosion products. Surveys have detected odd gravitational features in seafloor bulges that do not immediately match known structures, but in most cases these are associated with buried volcanic ridges or faulted blocks. As with other kinds of evidence, the more scientists look, the more natural complexity they turn up, and the less room seems left for clear technosignatures. Still, the ocean remains an attractive realm in which earlier civilizations might have either flourished or hidden. It offers stable temperatures at depth and protection from many surface catastrophes. It also offers for any later investigator one of the best chances for preservation because its deepest sediments are among the slowest changing environments on the planet. That combination of stability and obscurity makes every core pulled from abyssal mud more than a simple climate record. Each one is also implicitly a test for the presence of unusual patterns of metals or sudden changes that do not fit orbital rhythms or volcanic pacing. So far, the tests have revealed only the intricate workings of water life and rock. Yet each new meter of core extends the search a little further back into times when, if the Silurian suggestion holds any reality, other minds might have lit their own brief lamps beneath ancient seas and left a thin, nearly erased shadow in the slow rain of particles that now forms stone in the deep. Above the thin shell of air that clings to the planet, satellites trace bright lines against the night. They circle along paths calculated to keep watch over clouds, oceans, forests, and cities. Some relay signals, some scan the surface, some listen for whispers from deep space. Each is a small piece of metal and circuitry held in predictable motion by gravity and velocity. From the ground they appear as silent points sliding among the stars, brief visitors to any given patch of sky. In a matter of decades, human activity has turned near-Earth space into a new arena of engineering and debris, a loose ring of orbiting artifacts that did not exist before. If all of this were to cease, if ground stations went quiet, and factories stopped, most of the light objects in low paths would fall back within a few centuries, burning to plasma as they rejoined the air. Higher in geosynchronous belts and further out in graveyard orbits, other shells would linger for much longer, circling in darkness for tens of thousands of years before subtle tugs from the moon and the pressure of sunlight altered their tracks. On still longer spans, all but the most carefully placed structures would eventually drift or decay. To an observer arriving from some remote future, the near-Earth environment might hold only a faint residue of this brief technological storm. When minds working with the Silurian hypothesis turn their gaze outward, they ask what an earlier spacefaring civilization would leave behind. Natural satellites such as the Moon offer surfaces that do not weather quickly. There is no air to corrode metal, no running water to wash away dust. Footprints pressed into lunar soil during the current age will remain discernible for millions of years unless struck by meteorites. Larger constructions, if ever built, there would persist even longer. Yet over tens of millions of years, small impacts would gradually pepper and blur any exposed shapes, and slow movements of dust, driven by electrostatic forces, could soften their outlines. Buried structures would fare better insulated by regolith from micrometeorite bombardment and temperature extremes. If a prior technological culture used the moon as a workshop or archive, most of its surface installations would now be hidden beneath layers of impact debris, but subtle anomalies in local density or composition might remain detectable as oddities in gravity maps or in the echoes of radar pulses. So far, surveys have revealed basins, ridges, and lava-filled plains, all consistent with known geologic processes, though not every crater and hill has been mapped in fine detail. Beyond the moon, the inner planets present harsher conditions. Venus, with its dense hot atmosphere and active surface, would erase artifacts quickly. Mars, colder and thinner aired, offers better preservation prospects. Erosion there works slowly and wind scours rather than floods. Ancient riverbeds and lake basins still trace networks that formed billions of years ago. Rovers and orbiters have photographed layered sediments and dust-covered plains. They have also revealed curious rock shapes that for brief moments stir public imagination before more careful images and context place them within ordinary geology. For a structure to remain recognizably artificial over tens of millions of years, it would have to be either very large, very robust, or frequently renewed. Most likely, once its builders vanished, it would join the background of eroded hills and buried blocks. Still, the planet's thin air and long-lasting landforms make it a plausible site where remnants of a very old technological episode could hide in plain sight. On smaller bodies, such as asteroids, gravitational holds are weak. A modest push can shift an object from one path to another. If a civilization sought metals and volatiles, it might mine these bodies extensively, leaving geometric pits or patterns of extracted rock. Over great stretches of time, micrometeorite impacts and thermal cracking could soften these scars, but in some cases the altered shapes might endure. Modern missions have already shown that natural processes can produce surprisingly regular boulders, flat facets, and straight-edged fractures, reminding investigators that not every sharp line is a sign of design. The Silurian question, therefore, does not look for single striking shapes. It looks for ensembles of evidence, unnatural concentrations of certain alloys, repeated geometries aligned with orbital mechanics rather than with stress fields or regions where fine dust and regolith behave as if draped over hidden frameworks. It is here that the limits of current data sets enter. Only a handful of asteroids have been visited closely, and only small portions of the Moon and Mars have been examined on the ground. Much of the solar system remains a low-resolution map sampled by distant instruments. Across these distances, natural wonders and any hypothetical artificial remnants blend together as points and smudges. Another angle on the outward search comes from dynamics rather than from imagery. Long-lived structures in space must obey the same orbital laws as everything else. Certain special regions, such as gravitational balance points, offer particularly stable niches. Objects placed there, if not disturbed, can remain for spans that rival or exceed many geological cycles. This makes such locations natural places to check for unusual masses or reflectors, whether natural or manufactured. Probes and telescopes have scanned some of these regions and found dust clouds and small rocks. The results so far are consistent with expectations from natural celestial mechanics. Yet the mere act of checking marks a shift. It treats the local space environment as another possible chapter in Earth's technological history, no different in principle from an exposed cliff or an ice core. If long before humans sent their first radio waves skyward, another species reached for orbit, and beyond its efforts would be confined by the same gravitational wells and energy costs. Its rockets or other launch systems would place payloads in similar bands. Its desire for long-term stability would draw it to the same kinds of orbits. The difference would lie in the details, in what materials it used, in how much mass it moved, and in whether any of its constructs survived the forces that work slowly but inexorably on all things in space. Over time, collisions grind even large satellites into fragments. Solar radiation charges and moves fine dust. Planetary resonances tug on orbits. No artifact can remain entirely static. The absence of clear, persistent structures from ancient times in near-Earth space does not rule out previous spacefaring episodes. It merely constrains their scale and duration, suggesting that if they occurred, they were either modest, short-lived, or followed by enough time that their remnants have been thoroughly scattered. In this way, the sky above joins the rocks below as an arena where past and present intertwine. Telescopes scanning for debris and for natural hazards now also indirectly test the hypothesis that Earth's path into space is not wholly unique. The silence they find so far is not proof of solitude, but it is a kind of answer, one that frames any speculation about vanished starfarers in terms of what the cosmos does and does not preserve. The search for ancient industry often begins with side effects, with chemical and physical traces that no builder meant to leave yet, which endure more stubbornly than monuments. Another more deliberate possibility lies in the idea of messages. If a technological civilization foresaw its own end or simply wished to speak across deep time, it might attempt to design signals that survive longer than languages, cultures, or even species. In the modern age, humans have already begun to think in these terms. Engineers discuss how to mark long-lived nuclear waste so that no future digger mistakes it for treasure. Proposals range from forbidding shapes carved into the landscape to altered soils and specially bred plants that change color near dangerous sites. All of these are constrained by the same problem. Symbols that feel obvious now may be misread or ignored by minds shaped in very different contexts. This recognition pushes some thinkers toward messages that rely less on interpretation and more on physics. Ratios of isotopes, precisely arranged layers in sediment, and patterns in planetary atmospheres can be engineered so that any sufficiently advanced investigator, regardless of culture, will recognize that certain configurations are unlikely to be accidents. In principle, a civilization could choose to alter the abundance of a stable isotope in a particular element, raising or lowering it across part of the crust or ocean over many thousands of years. The resulting anomaly would outlast mountain ranges. Others imagine carefully crafted mineral deposits where the relative proportions of several elements encode numbers that are hard to explain by chance. All of this remains largely theoretical for humans who have only just begun to grasp how slowly geology writes and erases. For any hypothetical predecessors, however, the same logic would have been available. They too would have understood that ordinary artifacts crumble while chemistry remembers. If they chose to send a signal forward, they might have co-opted the very systems that geologists now rely on: the slow deposition of sediment, the cycling of gases through air and sea, and the long-lived stability of certain minerals. From the standpoint of the present, the question becomes whether any such deliberately structured anomalies have already been found, perhaps catalogued under other names. There are places where element ratios are strange, but these are usually tied to known processes, such as hydrothermal circulation or biological concentration. There are rhythmic layerings in rocks, but most can be traced to orbital cycles, tides, or the pulsations of ancient ice sheets. Each candidate so far has found a natural explanation more economical than the invocation of design, yet the very act of framing the planet as a potential message medium adds a layer of intrigue to ongoing measurements. A deep drill core that shows an abrupt global shift in multiple independent systems all coordinated across a short time becomes more than a line on a graph. It becomes in thought, if not in fact, a possible punctuation mark placed by intention rather than by blind eruption or impact. Another route to long-term messaging does not change matter, but changes probability. Natural processes have characteristic spreads of outcomes. River channels meander with certain statistics, crystal sizes fall into certain distributions, and variations in isotope ratios usually stay within defined bands. A civilization that learned to subtly bias these processes, nudging them again and again toward one side of their usual range, could in theory inscribe its presence not in any single striking feature, but in the overall statistics of landscapes and minerals. Detecting such a bias would require immense data sets and careful modeling tasks that 20th and 21st century sciences are only beginning to attempt. Beyond physical substrates, some speculative frameworks consider information stored in fields and correlations. Quantum properties, for example, can, in certain systems, retain echoes of past interactions. In laboratories, researchers coax fragile quantum states into acting as short-term memories or sensors. The idea that an ancient culture might have found ways to stabilize such states on macroscopic scales, turning parts of the planet into repositories of subtle correlations, stretches present understanding, yet it illustrates the breadth of the canvas. If intelligence once sought to speak across epochs, it had many layers of reality upon which to write. For now, most of the messages that humanity confidently reads in stone are those written by climate, by impacts, and by life's own chemistry. The rest of the record lies in numbers on charts, in peaks and troughs that can be shaded by different interpretations. The Silurian hypothesis does not claim that any one of these peaks is certainly a word, or that any trough is certainly a pause. It suggests instead that an entire mode of reading is missing, that the planet may hold in principle not only its own autobiography, but also annotations made by hands and minds long gone. Whether such annotations exist or not, the exercise of imagining them changes how present observers attend to the world. Layers cease to be just the outcome of blind processes and become also potential pages in a wider conversation, one that spans not merely cultures and nations, but entire cycles of civilization separated by millions of years. In laboratories and at field sites where cores are split and spectra traced, this possibility hangs at the edge of awareness, rarely stated outright, yet present as a faint question. If someone wished to be known across deep time, would this be how the attempt would appear, and would anyone recognize it for what it was? Across distant drill sites and scattered outcrops, researchers compare timelines drawn from ice sediment and stone. Again and again they see the same pattern. Different records taken from far apart places bend and tilt at the same horizons. A pulse of extinction in marine fossils arrives exactly where carbon isotopes swing, where grains in river deposits change size, where magnetic minerals freeze in new directions. These alignments reveal how tightly climate, oceans, and crust are coupled. To some imaginations, they also lend an uncanny neatness to certain transitions, as if invisible hands smoothed what might otherwise have been jagged. Natural systems can shift very quickly when slow pressures carry them to thresholds. Ice sheets sit in precarious balance until warmth undermines their roots. Then they rush seaward and vanish. Forests endure gradual drying until one season of lightning turns vast regions to ash. Yet in some stretches of the paleoclimate record, disturbances swell and then recede with a steadiness that seems almost gentle, as though some larger set of feedbacks cushion the blow. This perception may arise from missing data or from minds that prefer patterns, but it directs attention toward the subtle mechanisms by which Earth keeps itself habitable. Over decades of study, a view has formed in which life and the planet co-shape one another, a web of blind feedbacks rather than a conscious entity. Plants darken or brighten continents and pull greenhouse gases from the air. Microbes cycle nitrogen and sulfur, altering cloud seeds and ocean chemistry. Weathering of rock accelerates under certain climates, drawing carbon from the atmosphere more rapidly when temperatures rise. Together, these loops act as a kind of planetary thermostat, not perfect but persistent. Within this framework, the Silurian question adds a further layer. Might there once have been a time when intelligence joined these feedbacks, not merely as another participant, but as a planner tuning global systems on purpose and leaving behind self-running controls that survive its disappearance? The planet's magnetic field offers one possible arena for such thoughts. Generated by slow currents in the liquid outer core, the field shields the surface from much of the charged radiation streaming from the sun and from deep space. Over millions of years, its strength waxes and wanes, and from time to time it reverses north and south trading places. Cooled lavas on land and frozen basalts on the seafloor carry these flips as bands of opposite magnetization stripes across ocean basins and patterns in mountain belts. To present understanding, the timing of reversals looks irregular, driven by the restless fluid metal far below. Yet hints of long, quiet intervals and clustered episodes of change keep questions open. If a civilization ever sought to shape such behavior, perhaps to steady the field or to reinforce its shield, it would have to work with titanic energies and scales. No clear sign of such work appears in current data, but the very exercise of asking sharpens the study of how the field and the biosphere interact. Impacts from space form another canvas. Craters on Earth and on the Moon tell of a violent past in which large rocks and icy fragments struck often enough to reset ecosystems and at times to erase the majority of species. Over ages, the general rate of such collisions has fallen as debris is swept up or flung away. Yet the record hints at episodes when big impacts cluster, and others when long spans pass more quietly than simple models predict. Planetary motions, resonances in asteroid belts, and slow reshaping of orbits can explain much of this unevenness. A technological layer, if it ever existed, would add a different flavor, deliberate deflection and removal of dangerous bodies. Its traces might lie in families of asteroids missing expected members in gaps where particular orbits are strangely empty, or in a mismatch between the sizes of craters implied by models and those actually carved into old terrains. So far, incomplete surveys and natural explanations leave little room for firm claims. Still, every refinement in mapping near-Earth objects also tightens the constraints on any ancient program of celestial engineering. Climate itself remains the richest system in which to imagine long-lived intervention. In some intervals, temperatures and greenhouse gases wander within tight bounds for spans far longer than single orbital cycles, as though stabilizing forces quietly held them near values friendly to complex life. In others, ice ages come and go with clock-like rhythm, their advances and retreats marching to known variations in Earth's path and tilt. It is easy and hazardous to see intention in the calmer eras, to picture a society that learned to cancel out orbital nudges and volcanic surges by brightening skies, darkening lands, or drawing carbon from the air. Technologies of that sort are already sketched in modern proposals. Reflective aerosols, in the high atmosphere, vast forests, planted or removed machines that filter gases from air and sea. Sustained use of such tools would leave layered fingerprints, odd sulfur spikes in ice that do not match eruptions, pollen records that show abrupt coordinated shifts across continents, isotopic quirks tied to industrial processes rather than to fires or microbes. To date, most observed features of this kind fit reasonably within natural stories, yet there remain spans where many stabilizing trends overlap and details are not fully resolved. Beyond direct conscious control lies the quieter idea of inherited guardians. A civilization that recognized its own fragility might try to leave behind systems that watch and act on their own guiding key planetary variables towards safe zones long after their makers are gone. Fragile satellites and surface machines are ill-suited to such durations, but more deeply rooted devices might fare better. Concepts stretch toward machines anchored in old stable crusts, slowly modulating heat flow or stress to steer earthquakes and eruptions, or toward structures placed in particular orbits that for a while herd comets away from dangerous paths. Fields generated from buried circuits are imagined that gently steer charged particles or tweak cloud formation. These visions sit well beyond present engineering, yet they mark out a spectrum whose other end is the unassisted automatic feedbacks of air, water, and rock. If any such guardians existed, hints of their action would appear as correlations that defy simple models. Faults relieving strain just before more destructive quakes would be expected, climates halting their drift close to biologically favorable states, rather than overshooting ecosystems recovering from repeated shocks more easily than their structure alone would allow. At present, most scientists are cautious, preferring explanations that invoke no more than the known physics of fluids, fields, and evolving life. Still, the discipline of testing whether Earth's apparent long-term stability can be fully explained without recourse to past engineering deepens understanding. The planet is not assumed to be watched over by ancient devices, but it is examined as if it could be, with every stubborn regularity, treated as a puzzle whose answer may lie in volcanism, in orbital cycles, in biology, or conceivably in something more. Within that wide space of possibilities, the thought of earlier minds becomes one parameter among many, to be adjusted up or down according to what the rocks, the ice, and the skies finally reveal. At the smallest scales that instruments can probe, matter no longer behaves like a set of solid beads and levers. Instead, it resolves into fields and quanta ripples of probability that shift and interfere. Every interaction between particles leaves behind subtle correlations, and in principle these correlations carry information about what has happened. In laboratories, physicists cool atoms to near absolute zero and trap them in magnetic and optical cages. Under such conditions, fragile quantum states can persist long enough to serve as memory. Patterns of spins and phases record measurements, process data, and then vanish when disturbed. Devices built on these principles promise new forms of computation and sensing, but they also hint at something more abstract, the idea that the fabric of reality itself could in some sense remember. In ordinary life, this memory is inaccessible. Thermal motion and countless overlapping interactions quickly scramble any coherent pattern, yet certain materials can shelter echoes of past events for surprising lengths of time. Imperfections in crystals hold the tracks of particles that passed through millions of years ago. Tiny dislocations, alignment of spins and trap charges, whisper of stresses and fields long gone. Research has already used these microscopic scars to reconstruct the timing of geological and cosmic happenings, reading minerals as if they were photographic plates slowly exposed by the universe. The notion of quantum archaeology grows from this recognition. It asks in careful speculative terms how much of the past is encoded in present correlations, and whether in thought, if not in practice, a complete record might be spread thinly through every grain of matter. Practical retrieval of such a record lies far beyond current methods. Even the gentlest measurement tends to disturb what it observes. Yet the question itself expands the frame within which ancient civilizations are considered. Intelligence, once it arises, does not remain confined to simple tools. It tends to push into these subtler domains, learning to manipulate fields' entanglement and the constants that shape how matter behaves. In doing so, it gains both new powers and new ways to inscribe its presence into the world. Modern experiments already demonstrate how quantum states can serve as sensors exquisitely sensitive to their surroundings. An array of such devices, if cleverly arranged, could in principle watch over vast regions, recording variations in temperature, pressure, and radiation in forms that are extraordinarily compact. A culture interested in preserving an account of its era might choose to seed such sensors throughout stable crust or deep ice, trusting that some fraction would survive the erosion of ordinary artifacts. Over millions of years, most would decohere their patterns, blurred by interactions and heat. Yet in particularly quiet niches such as the deep interiors of cold asteroids or the cores of ancient crystals buried in old shield rocks, traces might persist, faint but not entirely erased. At the same time, the fundamental constants of nature, such as the strengths of forces and the ratios of particle masses, appear remarkably well suited to the existence of complex structures and long-lived stars. Observers have long noted that small changes in these numbers could prevent galaxies, planets, or chemistry as it is known from forming. The prevailing interpretation is anthropic. Only in universes where conditions permit observers will observers arise to comment on them. A more daring speculation entertained at the margins of theoretical work imagines that such tuning could itself be the outcome of processes involving intelligence. In some models, the properties of new regions of space-time might be influenced by the states of those that gave rise to them. If so, civilizations advanced enough to shape those states might play a role in sculpting the statistical landscape of physical law. Under that view, the apparent friendliness of constants to life and thought could be, in part, an inherited artifact of prior cosmic engineering, a kind of selection carried out not only by blind branching of universes, but by choices made within them. The Silurian hypothesis focused on Earth brushes against these broader ideas only lightly. Yet they share a common theme: intelligence as both product and editor of the cosmos. From this angle, earlier technological cultures on Earth might be seen not just as local episodes overwritten by tectonics, but as contributors to patterns at deeper levels, perhaps in the arrangement of quantum fields or in the distribution of certain entangled states. There is at present no empirical handle on such possibilities. Measurements of constants across time have found within error impressive stability. Correlations beyond known forces remain hypothetical. Still, the interplay between quantum information and macroscopic history continues to be explored. Techniques improve for reading ever fainter tracks in minerals, for reconstructing radiation environments from defects, and for teasing out how much structure can endure across deep time in seemingly ordinary matter. In parallel cosmology, refines its picture of how space-time and fields evolved from earliest moments to now. Each gain in understanding of what nature does unaided narrows the domain in which any deliberate alteration might hide. If some prior intelligence did in fact leave its imprint at these fundamental levels, its work would be entangled with the same equations that describe stars forming black holes, evaporating, and vacuum fluctuations seeding galaxies. Its techno-signatures would not be separate from physics but built into physics. For the present inquiry, anchored to drill cores and fossils, such heights remain distant, yet the thought that even the smallest components of matter might in principle contain a record of everything that has been done with them adds a final layer to the sense of Earth as archive. The rocks, the ice, the air, and the living tissues are all views of this archive at different scales, each keeping part of the story. Somewhere between the spacing of atoms in an ancient crystal and the expansion of the universe itself, there may exist traces not only of how the planet has turned and cooled, but also of how often minds like and unlike the current ones have learned to read and write within that grand script. Whether such traces are ever practically recoverable is a separate question. For now, their possibility contributes to the overarching atmosphere of the Silurian exploration, a calm recognition that the past may be richer than any present method can fully reveal, and that even seemingly empty stone and silent vacuum could be in ways not yet fully grasped, crowded with the fading records of long-finished thoughts. As the layers of evidence, speculation, and unanswered questions accumulate, a wider pattern slowly comes into view. Across ice cores, ocean muds, mineral veins, and the faint debris of near space, the same theme repeats. Brief disturbances leave long shadows, and those shadows, when viewed from a great height in time, form rhythms. Civilizations in this vision become pulses in a planetary heartbeat. They rise, consume energy, rearrange matter, and then fade, leaving behind chemical wakes and altered landscapes that persist long after their names are forgotten. Most of what they build is perishable, yet the combined effect of their actions sinks deep into the slow workings of climate and crust. When researchers model such cycles in abstract, setting up equations in which an intelligent species discovers, fuels, grows, strains its environment, and then either adapts or collapses, they often see repeated waves. Each crest is higher than the last if some knowledge survives, or roughly the same if each fall wipes the slate clean. The real Earth, with its patchy records and tangled forcings, may or may not have followed any such pattern, but the possibility shifts how its history is imagined. Instead of a single straight line from simple cells to present industry, the story opens to the idea of multiple arcs, some perhaps cut short before they could leave obvious marks, others reaching levels that modern humans have not yet attained. In the speculative frameworks that push beyond geology into cosmic context, Earth itself becomes one node in a larger network of worlds on which intelligence has blossomed and receded many times. Telescopes already show that planets are common, that many stars host systems with rocky bodies in temperate zones. Future instruments may add hints of atmospheres and perhaps of industrial gases or night-side lights. Against that backdrop, the notion that Earth alone has hosted repeated technological episodes while the rest of the galaxy remains silent feels both special and unlikely. A more symmetrical view would see Earth as ordinary in this respect too, one among many planets where life and mind run through experiments, some ending quickly, some building legacies that extend far beyond their own biospheres. Within this broader frame, the Silurian question acquires a second edge. It is no longer only about whether earlier civilizations existed, but also about what their outcomes suggest for the prospects of any later ones. If patterns of resource use and environmental strain are governed largely by physical and biological constraints rather than by culture, then most young technological societies may face similar bottlenecks. They discover powerful energy sources reshape landscapes faster than slow feedbacks can compensate and confront the hard limits of their planets. Some may manage to stabilize their relationship with their environment, turning industry into a long-term, nearly invisible participant in planetary cycles. Others may fail, leaving behind sharp, brief spikes in chemistry and extinction, followed by long recoveries. In that sense, the deep record of Earth, if read clearly enough, could serve as a kind of statistical sample. It could show whether the planet has tended to tip into runaway states when pushed, or whether it has repeatedly returned from edges, perhaps with the help of feedbacks that do not rely on intention. At the same time, the idea of guardian systems of technologies built explicitly to protect future life from impacts, runaway climates, or internal conflicts adds a further layer. In the most imaginative sketches, ancient cultures that weathered their own crises and learned to manage their worlds gently might have turned outward, setting up networks of sensors and subtle interventions that operate on automatic. Asteroid deflectors, climate moderators, and information archives might be left behind as part of a cosmic commons tools meant to ease the path of any later civilization that reaches awareness. If such systems existed around Earth, their presence would blur the line between natural resilience and assisted survival. A meteor that misses by a fraction of a planetary radius might have been nudged by nothing more than resonances and chance, or by the faint shove of a machine placed long ago. A climate that halts its drift toward a less habitable state could be the work of carbonate-silicate feedback alone, or of devices that quietly adjust aerosol levels or ocean mixing. In practice, any such assistance, if it existed, would be extraordinarily hard to disentangle from the planet's own dynamics. Most scientists therefore proceed under the simpler assumption that Earth's past and present are guided only by known physics and by life's emergent behavior. The notion of unseen guardians remains a boundary condition in thought, a reminder that even apparent stability should be interrogated with care. Meanwhile, within human society, awareness of planetary limits grows. Measurements of rising seas, shifting rainfall, and shrinking ice bring the abstract curves of climate models into everyday experience. Discussions of sustainability, once marginal, move toward the center of planning. Technologies under development, from low-carbon energy systems to direct atmospheric manipulation, echo in faint outline the hypothetical tools attributed to long-vanished predecessors in speculative narratives. The difference lies in scale and in the depth of knowledge. Modern humanity is only beginning to understand the full complexity of coupled ocean, air, and ecology. Decisions are made within decades, often guided by immediate needs more than by multi-millennial visions. In this sense, the Silurian hypothesis acts less as a claim about what did happen than as a mirror for what is happening. It asks current minds to imagine how their own trace will look when compressed into a slice of rock a few centimeters thick. In that slice, all the arguments, laws, and stories will be gone. What will remain are altered ratios of carbon and nitrogen spikes, of novel compounds, remnants of plastics, and patterns of extinction and recovery in the catalogs of future paleontologists. That thought carries a quiet weight. It strips away surface detail and asks which features of the present are durable enough to matter on the longest scales. It also raises a final open possibility. If cycles of rise and fall have indeed occurred before, and if some knowledge from them has been preserved deliberately in durable forms, then present investigators might eventually stumble upon it not as dramatic revelations, but as modest anomalies that once reinterpreted connect to a larger design. Until or unless such a connection appears, Earth's deep time remains a landscape of puzzles that can be fully mapped only from one side. The other side, that of minds now gone, is inferred from shadows. Whether those minds were the first, the fifth, or one of many in a line is a question that the rocks, the stars, and the quiet mathematics of change leave open, inviting contemplation rather than closure. In observatories, clean rooms, ships, and remote field camps, the present civilization spreads out a growing collection of fragments from earth and sky. Slivers of rock from ancient cratons, vials of polar air, cylinders of ocean mud grains returned from asteroids, and streams of numbers from satellites all join in shared databases. Algorithms sift patterns from these diverse strands, seeking correlations that once lay hidden by distance or by the limits of human perception. Out of this work emerges a more detailed portrait of Earth as a system than has ever existed before. It shows a planet that has changed many times, sometimes violently, sometimes with slow grace, yet which has maintained conditions suitable for complex life for an astonishing span. Within that portrait, the current technological era appears as a thin, sharp line, a moment when one species becomes aware not only of its own history, but of the deep context that surrounds it. This awareness gives the Silurian question a particular edge. For the first time, a civilization on Earth has both the tools to probe deep time and the conceptual frameworks to wonder whether it is unique. Drilled cores and spectrographs provide data. Models and hypotheses provide lenses through which those data are interpreted. Most of the evidence still points toward a story in which industrial technology arises only once in the present age, after a long series of biological and planetary transformations. Fossils show no clear signs of past machines. Isotopes, while they swing and spike, mostly trace back to volcanoes, impacts, and biological revolutions. Orbital surveys reveal no indisputable ruins on Moon or Mars. The simplest reading remains that humans are the first to reach this level of complexity here, yet science advances in part by holding possibilities open until evidence decisively closes them. Within that space of openness, the Silurian hypothesis functions as a probe, testing how well current understanding can account for every abrupt shift and odd layer without invoking prior intelligence. Each time a previously puzzling pattern finds a natural explanation, the need for technosignatures in that context lessens. Each time an anomaly resists such explanation, however, it stands as a small flag marking terrain not yet fully mapped. The very act of checking whether Earth might have hosted earlier industries sharpens the grasp of its non-industrial past. Climate cycles become clearer, extinction mechanisms more detailed, and the interplay between life and rock more finely charted. In this way, even if no evidence of predecessors ever appears, the exercise will have deepened knowledge. At the same time, the present era itself becomes more legible when viewed through deep time. Industrial output is no longer only an economic or social phenomenon. It is also a geologic one. Its products and byproducts will sink into sediments, alter minerals, and shift isotopic balances just as surely as any flood basalt or asteroid strike. Current decisions about energy, land use, and waste thus translate into marks on the planetary archive. Future minds, whether human descendants, other terrestrial intelligences, or visitors from beyond, will read that archive and reconstruct this moment in broad strokes. They will see that a species arose that could measure ancient air in distant galaxies, that could rearrange coastlines and chemical cycles, and that did so with great speed. Whether they will also see evidence of a deliberate shift toward long-term balance, or only the sharp signature of a brief overshoot followed by collapse remains undecided. The Silurian perspective quietly emphasizes this choice. Without prescribing it, it suggests that if cycles of rise and fall have occurred before then, the present stands at a familiar crossroads. In some imagined pasts, cultures may have crossed that point and stabilized, leaving only soft techno-signatures woven into natural feedbacks. In others, they may have faltered, leaving jagged scars in the rock and little else. Because those hypothetical stories are not directly accessible, they function more as mirrors than as guides. The planet itself, in its layered memory, becomes both teacher and silent witness. It shows how sensitive climates are to rapid forcing, how resilient ecosystems can be given time, and how long it takes for even major disruptions to fade into new baselines. Against that background, the current civilization carries an unusual attribute, an ability to imagine futures framed by millions of years rather than by a few generations. That imagination is fragile and uneven, yet it exists. It allows planners and thinkers to ask what kinds of traces they wish to leave, what sort of horizon they would prefer to inscribe in stone. If any messages or guardians from earlier epochs are buried in the crust encoded in minerals or drifting in stable orbits, they have not yet stepped forward clearly. Their possible presence hangs instead as a quiet possibility at the edge of observation. Meanwhile, the one techno-signature that is undeniable is the one now being written, the altered atmosphere, the plastics in the sea, the metals and isotopes arranged by human hands. In laboratories where cores are logged, the people reading them are simultaneously authors of a new entry in the same record. This dual role as both archivists and subjects marks a turning. For the first time on this world, the makers of a geologic layer understand while making it roughly how it will appear. That understanding does not dictate what follows, but it does expand the range of conscious choice. Whether there were Silurian precursors or not, the present civilization stands at a point from which it can look backward through billions of years and forward in thought through comparable spans. It sees a planet that has endured heat and ice impacts and upheavals, and that has, through all of this, remained a cradle for complexity. It stands now with tools that can either destabilize or help maintain that cradle. The deep questions remain unresolved. How many times has intelligence sparked here? How often has it reached for the atom and the star? How many of those attempts left more than a faint chemical whisper? The rocks answer only indirectly with tilted layers and scattered anomalies. The stars answer with their own silence, punctuated by the faint hiss of cosmic background and the ordinary light of galaxies. Between those quiet immensities, a thin film of life continues to write unaware for most of its history, newly reflective now. Whether that reflection is enough to change the long pattern of pulses, or whether it will simply add one more brief line to the layered memory of Earth remains part of the mystery that the Silurian hypothesis gently and without resolution invites minds to ponder.